Hi, welcome back again. This is Mrs. Thompson. Today we're going to continue our lesson on functions. And specifically we're going to talk about the extremum of a function, so that's the minimums and maximums. And we're going to talk about when functions have symmetry, specifically even and odd symmetry. So let's get started with the extremum. We have mins and we have maxes, and there are two types. They can either be local or relative, or they can be absolute. Okay, so a maximum is a place, f of c, a place on the function, such that f of c is greater than or equal to f of x for all x inside whatever interval I'm looking at. So for instance, on a graph, let's say this is A and this is B, I might have some curve like this. Okay, so I'm only looking at this piece of the function right here, just this little piece. And that little piece is going to have a maximum right here, and this would be f of c. Okay, right here. And so I can get a place that's bigger than everywhere else inside that interval. Okay, so most of the time, so all the time on the graph, these are going to look like a peak. Okay, now to make it an absolute maximum, then it means that f of c is greater than or equal to f of x for all x in the domain of f. So in other words, it's the largest, the biggest that the function ever gets on its entirety. There's never anything larger. Okay, so relative or local minimums then are the exact opposite. So we're going to start with the local ones, and we're going to go on some interval I, we'll call it A to B, with C being in between there. Okay, f of c is a local min if f of c is now less than or equal to f of x for all x in the interval. So the picture for that one, let's call this A and this B. So our picture for this one, we might have a curve like this. And so I'm only looking at the stuff in between here. So we're only looking at this little piece of the curve, only that red stuff. It would have a minimum right here. Okay, so all of these local mins will look like a valley. Okay, and then finally, the absolute min is going to be a place, f of c, that is less than or equal to f of x for all, here's a shorthand for you, for all x in the domain of f of x. So this shorthand right here, this means for all. And then this one right here means element of or contained in. So there's a little shorthand for you. So let's see if we can find some of these things. So here's some pictures. Those are the easiest ones to spot. So on this picture, we have a peak and a peak here. So let's name those points. This one is at 2, 2. And this one is at negative 2, 1. And then we also have a valley right here at 0, negative 2. Okay, but then I notice that the function goes down forever and ever. Okay, so let's start with the peaks and valleys. So we have a relative or local max at at -2, 1, and 2, 2. Okay. Now, do we have an absolute max? Well, the absolute max is the one that is the biggest for the entire function. Well, that would be this one right here, because this is bigger than the function ever gets, because we're assuming it continues down forever. Okay. Then let's talk about the minimums. Well, first of all, we have this valley. That'll be a relative min at 0, -2. But we have no absolute min because the curve is going down forever. Okay, so it doesn't have a bottom. Okay, now let's take a look at this one. We only have one valley. So that point right there at the origin is going to be a relative min. Okay, then we have this endpoint here, which is actually the biggest the function ever gets. So that's an absolute max. Okay, now it doesn't look like a peak, a mountaintop, because it's an endpoint. Endpoints can only be absolute mins and maxes. Okay, in order to be relative, it has to look like a peak or a valley. It has to have things on either side of it, nearby it, what we would call in math world a neighborhood around it, that gets below it or above it. So endpoints can only be the absolute. Now this hole over here, this hole over here, can be neither, okay? Even if it was the largest, even if that hole was like way up here, it could not be an absolute, okay, or a relative, because I can't get there. The hole implies I can't reach it. So an endpoint that is open will never be a min or a max either. Okay, so let's look at the graphing calculator a little bit, because this is a good tool for us to use. And so here's a screen off of a TI graphing calculator, and I'm going to plug this function into my y equals. And I'm going to graph it. And I notice on this graph that it does have a minimum down here, and it should have a peak up here that I can't see. Okay, so how is the calculator going to help me find those? Well, if we go to the calculate menu, so that's going to use your second trace, will get you to this menu, and I select option number 3 for minimum, okay, or option number 4 for maximum. And it's going to ask me for a left bound, so I'm going to move the cursor about here. And then it's going to ask me for a right bound, so I'm going to move the cursor over here. And then it's going to ask me to take a guess. So what I always suggest to students is that they put their cursor on that minimum point and then go to the left and then go to the right. Now to do the maximum, you can't quite see it. So you're going to have to watch as you're using your arrows. You're going to have to watch for when it starts going down, and that'll give you a left bound. And then go back to the right until you start coming down again, and that'll give you a right bound. And then you just hit enter, and it'll give you that maximum value. And then you do it all over again, and you can find the minimum value. Okay, so you probably want to try to practice it that a little bit. It's a useful little tool to help find them when they're not very obvious. You can see both of these are long decimal approximations. Okay, so now what about symmetry? Well, there are really two types of symmetry that we're going to talk about. One would be something that is centered on the y-axis. And this is called even symmetry. Okay, and this means that any point here is going to get flipped to the opposite side of the y-axis. Okay, The other type we want to talk about would be a curve that looks something like this. So some point is actually going to get flipped to its exact opposite. So in this type of symmetry, quadrant 1 points will mirror themselves in quadrant 3. Okay, quadrant 1 to quadrant 3. In quadrant 2 points, if there's one over here, it will get mirrored down to quadrant 4. Okay, and this is called odd symmetry, and it is symmetrical about the origin. Okay, now how do we know if a function is having either of these symmetries without looking at their graphs? So what we're going to do is remember, even means I get the point negative x, y. Odd means I get the point negative x, negative y. So what we're going to do is we're going to find f of negative x. And we're going to see what happens. Does it give us the original y back, or does it give us the opposite of the original function back? So we're going to plug negative x in. Okay, and then we're going to simplify that. So if I take a negative to the 4th power, that'll make it positive. If I take a negative and I square it, that also makes it positive. And so what I ended up with is exactly what I started with. Okay, if these two things are equal, this means I am even. Okay, so even means f of negative x equals f of x. Okay, so let's do another one. In this case, f of negative x is going to become 1 over negative x cubed plus negative x. So when I cube a negative, it becomes negative. And then this single negative. So what I ended up with is the exact opposite. That negative sign can go either on the bottom or out front or even up top. So that's exactly the opposite of what I started with. Okay? And so this is odd. So in this case, f of negative x equals the opposite of f of x. Okay, so let's do another. Here, I can take f of negative x. So I get 2 times negative x cubed plus 1 over negative x. Cubing that negative makes it negative. And this negative here in front of the x can just make it a subtraction. So this equals exactly the opposite of what I started with. So again, that's odd. Okay. Now in this case, if I find f of negative x, I'm going to end up with the square root of negative x plus 1. Now, this one has a domain of x greater than or equal to 0. So that's the only values I can talk about. So if I'm using a negative x, that's going to make it a negative number. So this is imaginary. So this is undefined on the real numbers. So this has neither symmetry. Okay, I didn't get the same as f of x, the same as what I started with, and I didn't get the opposite of what I started with. Okay, let's do another one. So this one, if I do f of negative x, I'll get negative x squared plus negative x minus 1. So squaring the negative makes it positive, but the singular negative changes it to subtraction, and the 1 here stays with subtraction. So this is not equal to f of x, and it's not equal to negative f of x. So this is also neither. Notice I had an even exponent and I had an odd exponent. So a lot of times when that happens, we end up with neither. Okay, but you want to verify it and make sure that we're not causing a problem. Okay, so because sometimes in these fraction ones, we can still end up odd. Okay, let's look at this last one. So let's take f of negative x. So that's 1 over negative x squared. So that's 1 over x squared, which is exactly what I started with. So this one is even. Okay, so it just takes a little practice. This is how you prove this symmetry algebraically. We want to actually show it because just looking at a picture, we're not seeing the entire function, right? We cannot zoom out enough to see it all. So this verifies that what we're seeing is always true. Okay? All right. So get some practice with this. If you're on my website or you're in class with me, you'll have the worksheet, the practice sheet to get some practice. And we will just look at it some more in class. If you've got some questions for me, feel free to comment down below. And we will see you next time.